ये कर किस चीज का रिकॉर्ड So this PDF is actually the digital lectures of Himanshu Agarwal. So here's I just revise this PDF and maybe some concept I elaborate in this video. So first, in digital electronics, like digital versus analog signal here. So basically, analog signals are continuous and also it's change with respect to time. And here is the some analog signal. This is also analog signal, and this is digital signal. Digital signal. So this is analog signal, and this is digital signal. Continuous amplitude, so analog signal, and discrete amplitude, digital signal. Now, biggest advantage of digital over analog. So here analog, uh, biggest advantage of digital over analog. So discretized and magnitude. So 0 or 1, 1 to 2, 3 to 3. So like this, like you can see here, 1, 2, like that way. Only digital signal flow with respect to time. Transmitting a signal analog 1.72 volt and where some drop I think plus 0.03 volt plus so 1.75 volt in digital L2 1.72 and it plus 0.32 so L2 also be better in noise performance easy to store. So, okay, better in noise performance and easy to store in binary and digit logic level and digital waveform. Generally in digital system there are only two possible state, either high or low. For high state, usually uh, 1 or 5 volt, or for low state, in both case that is 0 0. And digital systems such as computers can only understand 1 or 0. This two number system is known as a binary number system, and it's two digits 0 and 1 are called bits. A digital waveform, so rising edge, so here is rising edge, this is rising edge, and this is falling edge and rising edge, and this is pulse width, so what in which time the signal is high, so that times pulse width. Rise time taken to go from 0 to 1, so actually rise time is time taken to go from 0 to 1, 0 to 1. So this is rise time, and rise time is 10% to 90%. Basically, this time is called rise time. And fall time. So time taken to come from 1 to 0. So this is basically fall time, and fall time is 90% to 10% of the signal, like when falls. And ideally, rise time equal to fall time equal to 0 second. Basically, ideal case, so falls like where my slope is infinite and this is rise like this. But practically digital waveforms will have some finite rise and fall time. So here we can see, so this is my signal which actually not like slope is not infinite, so the slope is look like this, and slope from 10% to 90%, so in this period is called TR. So this is rise time. So this is called rise time, and signal from this 90% to 10%. 10% here. So this is not 10%. So this is actually the fall time. So this is TF. So and this width. So basically from here to from here, this is pulse. This is my pulse width. And periodic digital waveform. So time period. Okay, this is my periodic here. Like after certain time, like the clock cycles will same in each every cycle, and like it repeat after a times. After a times mean, so this is my one clock cycle. Sorry, not this. This is my one clock cycle from here to here. This is my team. Again, this from this to from this. So this is my another clock cycle. So that is T again. So this is my basically the periodic digital waveform. And here again you can see this is my again another clock cycle. So time period T, the time window at which the waveform is being repeated. So for time period, basically the time window at which the waveform is being repeated. So if I take this window, so the signal will repeat it again. The same window that I reflect here, my clock will repeat it again. And non-period digital waveform. So there are not a particular sequence follow in this region. So basically, if my here some random movement is happened. So this is my non-periodic digital waveform and duty cycle ratio. So basically, duty cycle is now suppose this is my clock. This is my clock signal, and this is so basically if it is my clock cycle. So from here to here, it is 100%. Okay. And how much time does this clock will on? So it's supposed 20%. So duty cycle is uh, the time at which the clock is on or the signal is on. So that time, so this is 20%, and the total cycles time, like cycle time is like total cycle or one cycle. So that is my 100%. So basically it is 20% or 0.2. This is my duty cycle. This is my duty cycle. So here the 0 to 1 and it is 10. So this is 1 by 10. The for given waveform find pulse width is 1, pulse width is 1 second, time period is 10 second, frequency is 1 by 10 second, and duty cycle is 10%. So all the things are correct. And clock. So an electronic logic signal which oscillates between a high and a low state at a constant frequency and ideally have a duty cycle of 50%. So an electronic logic signal which oscillates between a high and a low state at a constant frequency and ideally have a duty cycle of 50% and time period of the clock equal to t and frequency of the clock f is equal to 1 by t. So 50% duty cycle means like our clock which actually high at the 50% of the clock time and low 50% of the clock time. So here you can see the our clock that is 50% times high and this time our clock is low. So data sequence, the electronic representation of an information in terms of bits. So data sequence, what is data sequence? The electronic representation of an information in terms of bits. A random data sequence, so like this, So this is like data sequence, and data rate 2 bps, beat per second. Data rate is 2 bps, that is beats per second. So data sequence, the electronic representation of an information in terms of bits. A random data sequence 0 1 0, or like triple one, what is that? A big number, that is zero, either zero or one. So that is my data sequence. And data request 2 bps, that is bit per second. 2 bps 1 second equal to 2 bps, so 1 bits equal to half second. So here 2 bps 1 second in 2 bits, so 1 bit takes 1.5 second. So this is my clock, like not clock, here 0.5 second and 0.5 second, so half and half, something like that. Make a clock and data sequence given that clock frequency and data rate are 100 megahertz and 100 mbps. Take any random data sequence. Okay, so what he or she do, like clock is 100 megahertz, so 10 to the power 8 hertz. This is my clock, and time equal to time, so 1 by 10 to the power 8 hertz means 1 nanosecond, I think 10 to the power minus 8. So 10 to the power minus 8. Okay, so 10 nanosecond, sorry, 10 nanosecond. So my clock period is 10 nanosecond, and my data is suppose 1001, 1001, 0 double 0 triple one and triple one zero, like this. So 10 nanosecond up to here, this is 1 1, sorry, 0 0 0 0. Okay, this is my 0, this is my 1, this is 0, this is 1. So data rate 10 to the power 8 bps, 1 second 10 to the power 8 bits, 1 bit 10 to the minus 8 second, 10 nanosecond. So like this way the data goes. A data line is shown 2 microseconds, 0 to 2, 2 to 4, 6 to 8, and 10, like this way. So not a clock, data sequence. Find the data rate in mbps. mbps, that is bit per second. Okay, so 1 bit time period is 2 microseconds. 1 bit 2 microsecond, 1 in 1 second, 1 by 2 micro. What is this? 1 bit takes time, so 2 microseconds. So 1 bit take time, so 2 microseconds. So in 1 second, 1 second 0.5 m bits, megabits. Okay. Okay, here is micro. So in 1 second, 1 by 2 micro means 10 to the 6 by 2 bits or something like that. So 10 to the power 6 is mega, so in 1 second 0.5 megabits, so data rate is 0.5 mbps. And here is the 0101, so here is 1 by 4 micro, that is 0.25 mbps. That is wrong, I think. Here's the 10 nanoseconds, so clock t 10 nanosecond. Any random data sequence. Your data rate is 0.5 Mbps, 1 bit 2 microsecond, 1 second to 1 by 2 microsecond, 1 second 0.5 mbits. Data rate 0.5 Mbps. 01 01 01 01 01. So 0.25 Mbps. So building a digital system, logic gates, basic building blocks of any digital system. So digital system, and here is the building block. So digital system means, suppose we want to mm, make a adder. So adder is a digital system, but how we can make adder? So there are some block. Maybe we can use XOR gate or something like that. So that's maybe some block. Or if I using a full adder by using half adder, so half adder is like building blocks. And basic gate, and or not buffer, this is my basic gate. And what is universal gate? Universal gates basically two types. Two, not two types. So basically two, only two have two are universal gate. First one is NAND gate, here NAND, and second one is NOR. So why these gates are universal? Because if we want to make any basic gates by using these gates like NAND and NOR, we can make any basic gate. So that's why this name is universal gate. And arithmetic gates, basically for arithmetic operation, we are using these gates. So basically XOR and XNOR. And basic Boolean algebra concept here. So one or zero. So or operation is one or one, zero or zero, 1 1, and operation here you can see. So like for arithmetic operation, like for Boolean algebra, this is one. But suppose somehow arithmetic operation, so we can add simply. So that's the difference between arithmetic and uh, binary operation and Boolean algebra type of things. So remember, binary operation and Boolean algebra totally both are different. So one array, that is one, a and zero, this is zero. So zero bar one and one bar zero. So this is just like the basic, and here is the AND gate. So we know basic, so still we are revise it. AND gate output will be logic high when all the inputs are logic high. That's we know. So, and here is the AND gate symbol and the truth table of AND gate. So everything is zero. If the both input is one, then my output is one for two input AND gate case. And this is a three input AND gate. So only one when three input of AND gate is one. Otherwise, my output is zero. So basically on condition, so it's like just like a switch type of behavior. So it is on, then this symbol. If it is on, then open circuit type of things. For n input, total possible combination is obviously that is 2 to the power n, and switch represents representation of two input and gate. So this is just like two input and gate switch representation. Here is the bulb is glowing if the S1 and S2 both are on. Otherwise, it is off. Here is OR gate. So output will be logic high when any of the input is 1. Any of the input is logic high. So here my symbol is look like this. This is just like this. And input is A, B here, and output Y is equal to A plus B. And my truth table is here. If any input is 1, then my output is 1. Otherwise, if my all input is 0, then my output is 0. So this is OR gate, and 3 input OR gate is look like this. Here just same, just here 3 input, and here is the output. And this is my truth table of 3 input OR gate, and the behavior like the switching representation of 2 input OR gate. So just like this, here is switch. So if any of these S1 S2 is on, then my bulb is glowing. So it's like parallel combination of a switch S1 and S2. Concept of delay. So basically, if my AND gate 2 input A and B. So if it is identical, the gate is identical or ideal, then in ideal case there are no delay. Whatever the input, suppose this is my input A and this is my input B, both are on at the same time, so my output should be like this for ideal case. But what happened, there are some delay that the part of transistor, like digital IC design, so there are some, we know there are some delay will be happen, maybe 5 nanosecond or something like that. So we know the output should be like this, but due to some delay, it's little bit delay will be happen here, and the output look like this. So this is the part of basically digital IC design part, like how delay. So some kind of logical effort or parasitic delay and electrical effort. This kind of effort we are studying in digital IC design, and there we understood that how the this AND gate, NAND gate, or any gate we are designing, the how delay comes. Just because of I give you small concept here. There are a resistor and capacitor are present. So for resistor capacitor, they are like charging and discharging concept is there. So that's why the delay is coming. For t greater than 0, a equal to 1 and b equal to 1. For t less than 0, a equal to 0, b equal to 0. So here the concept, here the delay. So this is the delay concept. So now comes to the NOT gate. So basically NOT gate has one input, so and one output, and output will be logic high when input is logic low, and output will be logic low when input is logic high. So symbol is just like this. My symbol is just like this. So this is the truth table and switch presentation. So if my input is high, then my output should be 0. So this is the bulb, and this is my like this. So if my input is high, so input high means switch is on. If my switch is on, so then all the current go through this, and according across the bulb my voltage is 0, so there are no output. And if my switch is 0, then my output is 1. So this is the concept, basic concept of uh, NOT gate in switching representation. Now comes to the buffer. So buffer is basically output will be logic high when input is logic high, and output will be logic low when input is logic low. It's basically the some delay we add in a circuit, so that is representing by buffer, and nothing more than that. What is the input that will shows on the output after some delay, and this is the symbol that's I already write. Buffer is used to introduce delay and avoid latching effect. Yeah, sometimes buffer helps to avoid latching effect. So for that reason, we add latching like buffer. Now switch representation. So switch representation is nothing but just a switch. If my input is 1, then my output is 1 after some times. So they just like this. And conclusion of switching representation. xyz, so xyz something like that, x, so x plus y plus z also is something like that. So this is my switching representation. So here the one problem. So if both circuit are equivalent, then find x terms of a, b, c, d, e and f. Okay. So if my both circuits are equivalent, then find the x. Okay, equivalent. So okay, this is nothing but first a plus b into c plus d. Okay. If all the input either a, c, a, d is on, then my output bulb will be 0. So I write this way, and plus e f, and if everything is, this is my output y. Okay, so this here my output. So if my a, either a or c or a or d, like any input, like this way my can be circuit will be off, either this way my circuit will be off. Okay, now change the pen. Either this way my circuit will be off, either this way my circuit will be off, or either this way my circuit will be off. So basically this is the y, and now my y is just like x. Y is x. So what is x? X is equal to this. So let's see. Yeah, you can see here that this is my x here. So two not gates in cascade, so that is like buffer. So even number of not gate in cascade, so y is x. Three not gates in cascade, three not gate in cascade. That is that is also a look like not gate basically, but delay is increasing here. Odd number of not gates uh, in cascade, y equal to x, and here 2 nanosecond delay and 3 nanosecond delay, so that my its circuit look like buffer and td equal to 5 nanosecond. Nothing but these two is increasing just for adding for buffer, and the also like used as a buffer, and td 2 nanosecond and 3 nanosecond, so total 5 nanosecond. And concept of multi vibrator. So electronic circuit which implement two stage system like oscillation, timer and flip flops. So astable multivibrator, so no stable state, not suitable, no stable state and not suitable. Astable multivibrator. Astable, no stable state and suitable. So here is 1 0 1 0 like this. Trigger for triggering purpose like this. Monostable multivibrator, only one stable state like this. Stable state is here. And bistable multivibrator, so two stable state here. Bistable multivibrator, here's only trigger is at one condition, at one position, so this is, and here is trigger only one, trigger one like this, and this is stable state. and two stable state. So here also stable state, and here is my also stable state, like triggering is happened. So this is my bistable and this is my astable. Astable means only positive edge it will be triggered. Bistable means like my circuit will be triggered at both, and monostable is only one stable state. That's the only. So what if, like whatever the input 0 1 we give and 0, something like that. So 5 nanosecond delay, after 5 nanoseconds so it's initially 1, after 5 nanoseconds it goes 0 to 5 nanosecond, but after 5 nanosecond it goes again, so something like that. So my initially it's 0, so initially it's 1, after 5 nanosecond it goes to 1. So after 5 nanosecond, initially it changes, like a is changes from 0 to 1, so it will be changes after 5 nanoseconds, so 1 to 0, because it not gets, so 1 to 0 after 5 nanoseconds, and again when it is changes, so that time also we it changes after 5 nanoseconds, so it's delay. So this is a stable multivibrator, and this is called ring oscillator. A stable multivibrator, and this is called ring oscillator. Frequency of oscillation, so F equal to 1 by 2d. So basically 2d is nothing but 5, so 1 by 10 into 10 to the 9, so this is 100 megahertz. 100 megahertz multivibrator ring oscillator, astable multivibrator ring oscillator. Here also we can see that it is 7 nanoseconds, so basically 2 nanosecond, 3 nanosecond, 2 nanosecond, that is 3 plus 4, that is 7 nanoseconds. So after 7 nanosecond that circuit will change again, so here like this, and this is my a astable multivibrator, which frequency is 1 by 14 into 10 to the 9, so which is actually basically 71.42 megahertz. And here is the one of the questions I think Himanshu takes from gate exam. So basically 4 NOT gate will be present, but the thing is the circuit uh, takes the input from his own output of 3 after 3 NAND gates. So here is the my circuit takes the input and it will change. So we count only 2 nanosecond, 3 nanosecond and 2 nanosecond, that is 7 nanosecond. So after 7 nanosecond the circuit will changes. So here is the 7 nanosecond and here is 7 nanosecond. So this is the logic, but sometimes what others do that they are counting like these 2 nanosecond also. But this will not the, we are not taking the input from here. We are taking the input from here. So it's the remembering point, and basically this 3 not get delay, we just count and that is 7. So after 7 nanosecond it will changes and it looks like a stable multivibrator again. And frequency that's F equal to 1 by 2 into 7 nanoseconds, so that is 71.42 megahertz. And here is the again the same problem. So here is 2 nanosecond, 3 nanosecond, 2 nanosecond, though again the circuit will F equal to 2 into 7 into 2. So basically 7 nanosecond, after 7 nanosecond it will circuit will changes. Even suppose initially my 0 1, here 0, here 1, um 0 1, so this goes to 1 here, so this 0 will now change to 1, and this circuit will left out. So no matter what, we don't depend on A. So that's why my circuit output frequency is 1 by 2 into 7 nanosecond, that is 71.42 megahertz. Here is also the same 2 nanosecond, 1.5 nanosecond, and 2 nanosecond, that is 2 to 4, so 6.5 nanosecond, and here is zero point 0.5 nanosecond extra, that is 7, I think 2 to 4, 4 and 1.5. So 4 plus 4.5, no, 5.5 plus 0.5, 6 plus 4. So this is 10. So the changes is like 1 by 2 into 10. So basically it's 20. So 20 means 50 megahertz. 50 megahertz. Okay. What if A equal to 0? What if A equal to 0? Trigger 1 1, trigger 0 TD. So 0 what, double 1 0 0. So A equal to 0. So after TD delay, what is the TD? TD is basically the delay, even number of inverters there. Okay. So first in the A is the input. So whatever the input, that will follow the output, but the condition is one, that after TD delay. So here T1, here T1, but after TD delay, the circuit follows. Like circuit will always follow, but there are some TD delay is present, and this is monostable multivibrator. So basically, buffer makes a circuit a monostable vibrator, and the NOT gate basically makes the circuit like, or output makes a, or looks like astable multivibrator. So even number of inverters, that is called buffer. For delay, like we want more delay, so that's for. And the in even number, I think that there are no such kind of frequency concept is there in even number, because only once time the circuit will on, and rest of the time circuit will be maybe on or off, but it only one times like off on, rest of the time it is off. And frequency of oscillator, so a stable multivibrator is like oscillator. So if equal to 0, no oscillation here. Why no oscillation? Basically, okay. So basically here no oscillation, just because we add to NOT gate and one buffer. So the here is the problem actually created. I thought this is my NOT gate also, but this is not. So that's why like here frequency also 0, like no oscillation. Here also circuit behaves like uh, astable monostable multivibrator. Now this is De Morgan's theorem. So if my A and B and whole bar, then we can write this way. So basically A and basically it's NAND, AB NAND. So we can write like this way: A bar, B bar, A bar or B bar, and vice versa also. A B NOR equal to A bar and B bar. So this is the De Morgan's theorem. Some important point, that is we already seen A into 1, that is A, A, and A or A, this is A. So here A and A bar equal to 0, and A plus 0 equal to A plus 1 equal to 1, and A plus A bar equal to 1. A plus A bar equal to 1 means, suppose my A is 0, so then A bar is 1, because A equal to 0, so A bar equal to 1. So 0 plus 1 means 1, and here again my A into A bar, so 0 and 1, or 1 or 0, that gives me the output 0. So NAND gate, so this is my NAND gate basically, A B bar, so output is A bar plus B bar. And what is this? This is also my NAND gate. So this is actually called bubbled OR gate. Bubbled. So here is bubbled, and this bubbled is like just behave like NOT gate. So my A bar plus B bar. So the NAND gate and bubbled OR gate both are same, and here is the truth table. What is the truth table? So if my A and B both are 0 0, so for 0 0 AND gate is 0, but AND gate, like just AND gate and one NOT gate, and here is A and B. So if my A and B is 0, so here is 0, but 0 goes to here, this is 1. So 0 0 1. So what the NAND gate output? So basically if my input A, either A or B, one input is 0, then my output is 1. Or if my both input is 1, then my output is 0. So this is the concept of bubble OR gate or NAND gate. Here again three input like switching circuit we make, and of two input and NAND gate. Here is the three input bubble OR gate or three input NAND gate. The concepts are same. And here is the NOR gate. So in NOR gate we can represent like this, a plus b bar, but also it is a bubbled NAND gate. So basically a bar into b bar. So in De Morgan theorem we see that NOR of AB is also, we can write a bar into b bar. So this a bar into b bar is just like this, a b. So my output is a bar into b bar. So this is my bubbled AND gate. And here is the truth table. If my both input is 0 0, then my output is 1. Otherwise, if my one input is 1, then my output is 0. So how it's worked? Basically this is OR gate. So A and B, A and B, and then we take a NOT gate. So this is my output. So suppose my both input are 1, then my output is 1, because this is OR gate. And now this one goes through a NOT gate, so output is 0. So that's the reason. If my any input, like suppose 1 0, then also 1, and then my output is 0. But suppose both input are 0 0, that times this one converts to 0 and this one converts to, this 0 converts to 1. So that time only 0 0 times, that times 1, otherwise everything is 0. So this is my switching circuit. So basically the whatever we studied that the about NOR gate. So this is my switching circuit. So A plus B whole bar. So in parallel across the bulb. So this is my switching circuit. So OR gate is how look like. OR gate is my like look like this. Sorry, this is my switch, and this is my bulb, and this is my voltage supply. This is DC voltage supply. So my bulb will be on. So this is my OR gate. Now why NAND and NOR gates are called universal gate? So uh, previously I already told that with the help of AND or NOT gates combined, you can design any Boolean function. With the help of AND or NOT gates, you can design any Boolean function. But using NAND or NOR gate alone, you can design all the basic gates, AND or not. So basically, you can design NOT gate by using NAND gate, by using NOR gate. You can design AND gate also by using NAND gate or NOR gate. You can also design OR gate by using NAND gate or NOR gate. So alone enough to implement only any Boolean function. So these gates are alone can make any Boolean function. So that's why this is called universal gate. NAND gate is universal gate. So this is not gate. So we just sort the gate and we input A, So my output is y is equal to a bar. So this is my not gate. For AND gate, just like we take the NAND gate here, and NAND gate output we just like do the previous type of things, like just both are short circuit and we give the input, and this gives me the output as or behave like AND gate. Here is OR gate. How we make OR gate? So y equal to a plus b. So we just a bar plus b bar. So basically we take a y bar equal to a plus b bar. So if it is like that, so a bar into b bar. So this is my output, and after that what we do? Y equal to a bar into b bar whole bar. So here we do a bar here, a bar, b bar, and just we and these two are ANDed like NAND gate. We can use one NAND gate. So also NOT gate you can use using by NAND NOR gate. So here we make NOT gate by using NOR gate, and here is using OR gate by using NOR gate, and here we make AND gate by using NOR gate. So XOR gate. What is XOR gate? So output is logic high when both input are different. So both input are different. So either my A is 1, then if my B is 1, then output 0. But if A is 1 or B is 0, then my output is 1. If my B is 1 and output A is 1, then it is 0. If A is 0, then my output is 1. So if my both input are same, then my output is 0. And if both input are different, then my output is 1. So this is for a two input XOR gate. Dependent and same non-equivalent detector, only two input XOR gate. Okay, note three input XOR gate does not exist. So according to Morris Meno, so A B bar B A XOR B XOR C. So this is my three input gate XOR gate. So here is the solve, that 0, even number of 0, then 0, then odd number of 1, then it will be 1, and if 1 2 3. So if my odd number of 1, then my output is 1. If my even number of 1, then my output is 0. If my even number of 1, then my output is 0. If my odd number of 0, then my output also 0. So basically, if my 1, suppose I take 1 0 1 1, and then I take 0 and 0. So 1 1, that gives me 0, 0 1, that gives me 1. So when one number of ones comes, then also we get 1. This 1 0 1, this 1 0 gives me 1 output. So while one number of odd number of 1 are present, then only we get 1, otherwise we'll get 0. So XOR gate, Odd number of one is detector, ones detector. So we can also call odd number of ones detector.